Hello guys, good morning. You are welcome to my YouTube channel, the Explicit Tutorials, and my name is Tutor Joseph. In today's video, I shall be taking us Chem 111, Chapter 2, that is the second part of what? Chapter 2. A topic called what? Excuse me, isomerism. Isomerism can be defined as a process whereby two or more organic compounds have different chemical or physical properties. They have different chemical or physical properties. While these organic compounds that possess isomerism are called what? Isomers. They are called what? Isomers. Now, on a broad note, there are two types of isomerism. On a broad note, we have two types of isomerism. We have structural isomerism, and we have what? Stereo isomerism. So on a broad note, these are the two types of isomerisms that we have: structural isomerism and stereo isomerism. Now, first thing first, we are going to be discussing structural isomerism. Where is the board paper? Excuse me. We are going to be discussing structural isomerism. As the name implies, structural, okay? It is a type of isomerism that have the same molecular formula but this different structural arrangement. I'll repeat. I said it is the type of isomerism in which two or more compounds have the same molecular formula but different structural formula. That is, their molecular formula are the same, but the way the structures are arranged are different. Now, this type of isomerism is now subdivided into four. I think, is it four now or five? Now we have number one, we have the chain isomerism. I said structural isomerism is a type of isomerism in which two or more compounds have the same molecular formula but different structural formula. I said it is now subdivided into chain isomerism. Now, this is a type of isomerism in which compounds are arranged in different form, like maybe straight or branched, as the case may be. Let's take for instance pentane. You know, pentane is C5H12. This is pentane. Pentane has three isomers. Pentane has how many isomers? Three. Butane has two. Pentane has five. Okay, hexane has five. Then heptane has nine. Butane is two. Pentane is three. Hexane five. Heptane 9, octane 18, as the case may be like that. So I said this type of isomerism is based on the way the chain is arranged. It could be straight or branched. Let's take for instance, we have CH3, CH2, 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 and CH3. Now this is a normal pentane. This straight pentane structure. Now if I now have the branch time become CH3, C, then CH3, H, I have CH2, CH3. You can see now that it has this one is a branched pentane compound. Now this becomes, I'll start counting from your 1, 2, 3, 4. Now the substitutes is at carbon 2. It becomes 2, this methyl, 2 methyl, then 1, 2, 3, 4 butane. Alright, 2 methyl butane, because the substitute is situated at carbon 2. Now this number 1 isomer, number 2 isomer, I said it has 3 isomers. We now have CH3, 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 and CH3. 1, 2, 3, 4, 5. Okay. Now the longest chain here is what? Propane, like 1, 2, 3. And these two substitutes are found at carbon 2, right? It becomes 2 dimethyl. It is a dimethyl because of what? 2 methyl groups. Dimethyl what? Propane. So these are the stereoisomers of what? Pentane. Look at its chain. It has to do with the way the chain is arranged. It could be straight, branched, or what? Branched, like that. Now, number 2 type of structural isomerism is the positional group what? Isomerism. The positional group isomerism. In this type of isomerism, it has to do with the position of the functional group of a particular what? Homologous series. For example, if I have 3 carbon atoms, let me write it. 2 positional group isomerism. Now, if I have 1, 2, 3, 4, all right. If I have OH here, now this OH is what? The hydroxyl group. So if I want to name this compound, it becomes what? I'll start naming from here, counting from here. 1, 2, 3, 4. Now that you have the OH situated at carbon 4 at carbon 2, it becomes what? 2 hydroxy butane. 2 hydroxy what? Butane. Okay. I can also say but 2 O. Like, you know, it's that this O connote what? This OH. So I can say but 2 O or 2 hydroxy butane, like that. You see, the OH is at carbon 2. I can also start to do like this. 1, 2, 3, 4. I can bring it here. Okay. I can place it at this first carbon. Here it was what? 2 hydroxy. Then this one becomes 1 to but 1 O. It is but 1 O because the OH is situated as what? At carbon what? 1. You see, now it has to do with the position of what? The functional group of a particular homologous what? Series. Now number 3 is structural. Number 3 is what? Functional group isomerism. Functional group isomerism. Now, I said the chain isomerism has to do with the way in which the chain is what? Arranged. It could be straight or what? Branched. Now, this positional group isomerism has to do with the position of the functional group of a particular what? Homologous what? Series. Now, you now have what? Functional group isomerism. This is a type of isomerism in which 2 organic compounds have the same molecular formula, but they have different functional what? Group. I'll repeat. It is a type of isomerism in which 2 or more organic compounds have the same molecular formula, but different what? Functional group. Take for instance the aldehyde and ketone. If I don't call it ketone, I call it what? Alkanone. If I don't call it aldehyde, I can also call it what? Alkanal. Now, what are some examples of functional group isomerism? A good example is CH3, CH2, CHO, and I also have CH3, CO, CH3. Now, this idiot is called what? Propanal. This propanal, because of what? This CHO present here. Look at it now. Now, this one is called propanone. It's called propanone because of the alkanone functional group, which is what? This CO. Let us check. I said we said that they have the same what? Molecular formula, right? but different functional group. Now let's check how many carbon atoms we have here. 3. We have 1, 2, 3. That is C3. How many hydrogen? 1, 5, 6. H6, then O. Right? Then this we have how many carbon atoms? 3 carbon atoms. How many hydrogen? 6. How many oxygen? 1. Alright, you can see that the same molecular formula but different word functional group. This first one has aldehyde functional group, but this one has the alkanone or ketone functional group. Another example is the one that exists between ethanol and methoxymethane. Methane. Ethanol is CH3 CH2OH. Is what? Methanol. Then methoxymethane is CH3O CH3. Now, this ethanol, this O, I told you is from what? The alkanol functional group. This O here, it presents what? The alkanol functional group. Then the O here indicates what? The ether functional group. Let's check if we have the same molecular formula. 1, 2, C2, H5, okay, OH, C2H5, OH. I have C2H5OH. I believe I'm correct. Okay? No. Can also do it like this. 5. Okay, 5. Now, this O here connotes the alkanol functional group. That is OH, while the O here connotes what? The ether functional group. So please, ethanol and methoxymethane possesses what? Functional group isomerism. Propanol and propanol possesses functional group what? Isomerism. Please take note of that. It is very what? Important. Now the fourth type of isomerism is called tautomerism. 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 Now, tautomerism is a process whereby two structural isomers can undergo what? Dynamic what? Reaction. That is equilibrium what? Reaction. They can be what? Interconvertible. They can be converted either of the two ways. If I have H, I have triple bonds. This hydrogen what? Cyanide. Now, I have H. This carbon come over, becomes C, triple bonds, then this N. You can see now, this is what? A tautomeric what? Type of reaction. This tautomerism, it is what? Reversible. Now, this sign is a sign of what? Reversibility. Now, another example is the keto. I have H. Now, this OH here, okay, this CO, I told you before, this is what? The keto form. It is keto form because of what? The ketone functional group. Now, the same thing is applied here. If I have this H, C, OH, now, this one is what? Ketone functional group because of this idiot here. Now, this OH is for the what? Alkanol. So this is what? Enol form. Enol, that is OH, then Keto because of what? CO. Please take note of that. Now, another illustration of tautomerism is what I'm about to do. Let me rub up this one so I'll have enough space. Just follow it step by step, you understand it. Now, if I have CH3, if I have CH3, C, alright, let me put this as case A, then I'll now bring the other one as CH3, now the longest chain here is what? Butane. The longest chain here is what? Butane. If you want to start naming, we have to first thing first check where the functional group is. Now we have the first functional group at what? Carbon 1. This is the O8 functional group. The ether functional what? Group O8. You can see that ester, not ether, sorry, ester functional group. You know they are O8s like alkanoids. Now, if I want to name this one, I'm going to do it alphabetically. Now, this one is what? Ethyl becomes ethyl. This 1, 2, 3. All right. Now, this also, because of this O, becomes 3 also butanoids. Look at it. That is 1, 2, 3, 4. Ethyl, that is ethyl. 3 also, it is butanoids because of what? 1, 2, 3, 4. Because of this O8 what? Functional group. Now the same thing is applied here. This ethyl. Then this 1, 2, 3, 4. Ethyl. 2-hydroxy. 2-hydroxy. Boots 2 in. Alright, boots 2 in. Oh, okay. To be much more specific, let me do it like this. Ethyl boots enoids. Ethyl boots 2 enoids. Now, this ethyl, right? 1, 2, 3, 4. The OH is at what? 2. It is O8 because of what? This ester functional group. So please, this is all about what? Structural isomerism, which means that ethyl 3 also butanoids and ethyl but 2 enoids possess tautomerism. Please take note of that. Tautomerism. So it's like this. There's no, and it is what? A reversible reaction. It is reversible. There's no space, so I have to bring it down. So please, that is all about what? Structural isomerism. I believe what I've said so far was comprehended. I said that we have 2 types of isomerism, structural and what? Stereoisomerism. Structural is divided into chain, position, functional, and what? Tautomerism. Now we are about entering what? Stereoisomerism. Now, stereoisomerism is a type of isomerism in which 2 or more organic compounds have the same molecular and what? Structural formula, but the arrangement of atoms is what? Different. I recap. Stereoisomerism is a type of isomerism possessed by 2 or more organic compounds having the same molecular formula, the same structural formula, but different in what arrangement of what their atoms. Now it is divided into two. We have the optical isomerism. Okay, so no. Yes. Let me just bring. Should I bring geometric first? Okay, we have the geometric isomerism, and we have what the optical. Now it says stereoisomerism is a type of isomerism possessed by two or more organic compounds having the same molecular and what structural formula but different in the arrangement of what their atoms. It is divided into two: geometric isomerism and what optical isomerism. Now, a geometric type of isomerism is the type of isomerism that has the cis and what trans isomerism. It's a type of isomerism that has what the cis and trans what isomerism. Let me rub off this one. An isomerism is said to be cis when I have something like this. If I have COOH, COOH, H, H. Now, this type of isomerism in which the two substituents are found on the same side is called what? A cis isomerism. A cis what? Geometric isomerism. Now, but a type of isomerism in which the two substituents are found on different parts, like something like this. You can see one is up, the other one is down. So this is what? A trans isomerism. Now please, trans is a Latin word and it means what? Across. It's a Latin word and it means what? Across. Then cis is a Latin word, it means what? Come this side. They are by the side. They are just found side by side. Now this type of isomerism is called what? Cis butane. Okay, cis butene dioic acid. Alright, cis butene dioic acid, that is 1, 2, 3, 4. Butene, because of what? This double bond. Dioic acid, because of what? These two functional group of the carboxylic what? Acid. You now have what? This one is also the same thing. So it's transbutene dioic acid. Transbutene dioic acid. Alright, this one is called what? Malic acid. This is butene dioic acid is called what? Malic acid. While this trans butene dioic acid is called what? Fumaric acid. Right, so please take note of that. Then some they may occur in form of what? Ring. If I have something like this, H, I have CH3 here. Okay, I have CH3, I have CH3, this H, this H. How would you name this compound? How would you name this type of what? Compound. Now to name this type of compound, it becomes this 1, 2, 3. 1, 2, 3 is what? Propane. So just put it at the side of your mind. Now look at it. It's a cyclic compound. It becomes what? Cyclic what? Propane. Look at it. A cyclic compound has been formed. Therefore, this becomes 1, 2-dimethyl cyclopropane, 1,2-dimethyl cyclopropane. So that's how it is. Now, this one I've given you. Now, please take note of this. That is, compounds that undergo geometric isomerism, they have the same chemical properties but different physical properties. Take note of that. Geometric type of compound have the same chemical properties because of what? These double bonds that they have in common. And that double bonds is an atom or a group of atoms, a bond or group of bonds that are responsible for the chemical properties of what? An element. Please, they have the same chemical properties but different what? Physical properties. Take note of that. And please, because owing to the fact that we have double bond present in geometric isomerism, rotation is what? Limited. Rotation is what? Limited. And that is, it cannot rotate freely because of what? These double bond present in their, that is carbon to carbon what? Double bond. Rotation is what? Limited because of this what? Double bond. Unlike ethane, ethane has the staggered and eclipse type of what? Rotation. Staggered. If I have something like this, maybe I have this. Maybe I have something like this. Okay, let me do it very well. I have something like this. I have something like this. I have something like this. Let me differentiate this. Now, this one is called what? The staggered rotation. This one is called what? The staggered rotation. But because of this bond present here, rotation is not hindered. It means I can bring this one down, so this one will go up. It becomes CC. I have something like this. This one will still be here. This one will come down. This go like this. So this one is called what? Eclipse what? Rotation. So the staggered and eclipse rotation is found in what? 18, because they can easily what? Rotate. They can, if I should bring this now, now have what? This. So please, everything about geometric isomerism is what? Dealt with. Is dealt with. And the next one is what? Optical isomerism. I love optical isomerism. Now, please, all that I've said so far must be assimilated. It must be assimilated. Now, I said we have the other type called what? The optical isomerism. Now, please take notes. Optical isomerism or compounds that possess optical isomerism have identical physical and what? Chemical properties. Please. They possess identical physical and what? Chemical what? Properties. Take note of that. But in geometric isomerism, they only have the same chemical properties but different what? Physical properties. Now, for a compound to possess optical isomerism, such compound must possess what? A chiral ring. A chiral ring is a type of ring that joins to itself other substitutes, and as such it can what? Rotate easily. Now please, compounds are said to be optically active if they are able to rotate plane polarized lights. Optical compounds are said to be what? Optically active if they are able to what? Rotate plane polarized what? Light. And this rotation is based on what? The chiral ring. Please, the word chirality means handedness. The word chirality means what? Handedness, which means that for an optical compound to be able to rotate a plane polarized light, such compound must possess what? This what? Chiral ring. It is very, very what? Important. Now, is another one? Is another one? Now we now have, there are some compounds that do not actually form, or that form mirrors of each other. They form mirrors of each others, and these are called what? Enantiomers. Enantiomers are mirror formers. Enantiomers are what? Mirror formers. They are able to what? Form mirror. They are able to what? Rotate. Now, the combination of two or more enantiomers is called what? Racemic mixture or racemate. The combination of two or more enantiomers is called what? Racemic mixture or what? Racemate. Now, racemic mixture or racemates are optically inactive. Take note of that. Are optically inactive because the rotation of one enantiomer is cancelled or neutralized by the other one. Now I told you that the combination of two or more enantiomers is called what? Racemic mixture or what? Racemate. Fine. They are what? Optically inactive. Let me write again, please. They are optically what? Inactive because the rotation of one of these racemic mixtures would be neutralized or cancelled by the other one. Therefore, they are optically what? Inactive. However, if one of these enantiomers rotates, if it undergoes reaction, such reaction now produces a product that is the same as that of the second enantiomer. Such type of reaction is called what? Inversion of configuration. Racemic mixture or racemates, they are optically what? Inactive because the rotation of one of the enantiomers would be neutralized or cancelled by the other what? Enantiomer. I said, however, when one of them undergoes a certain type of rotation or reaction, and it brings about the product that is the same as that of the other, that is the other enantiomer, such rotation or reaction is called what? Inversion of what? Configuration. This type of inversion of configuration is called what? Optical inversion. Optical what? Inversion or Walding inversion. Their father. I said the rotation that one of them exhibits such that the product will be equal to the one the other one exhibits is called what? Inversion of what? Configuration. This type of inversion of configuration is called what? Optical inversion or Walding inversion. Please take note of that. Please, enantiomers are separated from one another through what? Resolution. Please take note of that. Enantiomers are separated into their component through what? Resolution. Okay, please, enantiomers are separated into their various components through what? Resolution. Take note of that. So that is all about enantiomers and mirror formers. They are able to rotate plane polarized what? Lights. Two or more enantiomers are called what? Racemic mixture or what? Racemates. They are optically inactive because rotation of one will be neutralized by the other one. But I said when one of them undergoes a type of rotation leading to the formation of a product that is equals to the other one, it's called conversion of what? Configuration. This type of inversion is called what? Optical inversion or Warden inversion. Okay, so and they are separated into their various components through what? Resolution. Okay, let me illustrate what I just said. It's good we illustrate something so that we know what we are trying to say. We will not just be talking out of imagination. So if I have this, if I have carbon atom like this, if I have OH, I have H, I have H, I have okay, let me put it here. Okay, HCl. Then, okay, let me just like this. CH2CH3. Okay. And this 1, 2, 3. Now this is what? 2-chloro, 3-hydroxy propane. Which now this is a normal compound. 3-chloro, 2-hydroxy what? 1 propane, right? Now it wants to rotate. It's about to rotate. In doing that, this OH will come this way. If a particular optical compound rotates to the left, it is called what? Level rotatory. Level rotatory. If it rotates to the left, it is called what? Level rotatory. But if this left is usually what? Anti-clockwise. Anti-clockwise. But if it rotates to the right, it's called what? Dextro-rotatory. If it rotates to the left, it is called what? Level rotatory, and it is what? That is left anti-clockwise. The normal clock rotate like this, okay, that is rotate to the right, and that one is what? Dextro-rotatory, and it is what? Clockwise. Right rotation, dextro. Left rotation is what? Level. Now, what is going to happen here? It's going to come like this. This OH that was by the right will turn to left, becomes OH. Now, this one that was here will turn to the left, becomes what? Cl. And now C2H3. Now, take notes. These are Chira rings or Kara rings. They do not rotate upwards or downwards. It is that right or what? Left. You can see we only have 2 Chira rings here, 2. Alright, so please take note of that. So another example is, I believe I can rub off this one. Even glucose. I have CHO, I have OH, I have H, I have H, I have OH, I have OH, I have H, I have H, CH2OH. 1, 2, 3, 4, 5, 6. That is C6H12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. O6. 1, 2, 3, 4, 5, 6. O6. So this is what? Glucose. If I want to do the rotation now, if I want to do the rotation, what will happen? This one will come this way, becomes CHO, H, OH, OH, H, H, OH, OH, H, CH2OH. You can see now that it has rotated. The ones that were by this left hand side have rotated to the right hand side. Okay, now the ones that were by the right hand side have rotated to the left hand side. So please, this is what. And glucose has how many chiral ring? 1, 2, 3, 4. So there are 4 chiral ring in what? Glucose. Take note of that. So the next one, please let me say this. Compounds which do not form mirror of each other are called diastereomers. Are called what? Diastereomers. They do not form mirrors of what? Each other. They do not form mirrors of each other. Now, then they are separated from one another via chromatography and fractional what? Distillation. They are separated from one another through what? Fractional distillation or what? Chromatography. They do not form image of what? Each other. Okay, if I have this, if I have something like this, H, okay, Cl, H, so doing it, I'll have H, C, okay. No, I'll not have Cl here. I'll have H, I'll have OH, we have H. If I should take the both of them to one side, I'll be out like this. I have H, I have OH, Cl, C2, CH3, H. If this one rotates, I'll be out like this. I have H, I have OH, I have H, I have Cl, I have H, and I have CH3, CH2, Cl, CH3. Now, let's observe something. Now, look at it here. This one, this Roman figure 1 and 2, they have what? They are enantiomers because they are able to what? Rotate, plane, polarize what? Light. Which means that whatever you have at the right hand side must not be at the left hand side. Initially it was by the right, but it now turned to the what? Left. It was by the left, it now turned to the what? Right. Which means that 1 and 2 are what? They are enantiomers. Look at now, they were by the right hand side, they now rotated to the what? Left hand side. So they are what? Enantiomers. So which means that 1 and 2 are enantiomers, then 3 and 4 are what? Enantiomers. But something is wrong somewhere. Something is wrong somewhere. Let's check. Okay. Second OH. Okay. Okay, let me do it like this. Cl OH, and I have Cl OH. Okay, better now. Now looking at what we have now, these two they are the same, and these two they are also enantiomers. These two are enantiomers. But if we should look at it properly, we are going to observe something. We observe that after the rotation, look at OH here, look at another OH by the left. Therefore, 1 and 2, that is 4 and 1 are what? Diastereomers. Okay, then which one again? Which means that 3, 2 and 3 are what? Another what? Diastereomer. Okay, so please, that is all about what? Isomerism. If you have learned something, please endeavor to subscribe, like, share, and comment. Now, my next video is going to be what? On chapter 3. Thanks for watching, and do have a wonderful day.